So the good news, I think, depending on your point of view, is that the first part of this lab, the first part of this lecture is pretty much a review. You've seen a lot of this stuff already. So let's begin. Simple harmonic motion. Now remember, you call this simple? Oh my God. All right, here we go. So this slide should look very familiar. So let's ask some of these warm-up questions. You have a sketch with 3 parts, top part, middle part, bottom part. When is the kinetic energy the greatest in this system? So you have a box on a spring oscillating back and forth. Remember, we call the position x equals 0 the equilibrium position. This particular spring has both compression and expansion. So with this box going back and forth, when is the kinetic energy of the system the greatest? I guess this is a good place to begin because you don't know.
Oh, I think I know. It would be in the middle box because
Right.
the kinetic energy is closest to the equilibrium.
That's right. When the box goes through equilibrium in either direction, it doesn't matter. Very good, Caitlin. Okay, so when is the potential energy of the system the greatest?
I guess in the top and the bottom slide.
Yeah.
Okay.
When the spring is stretched the most, and when the spring is compressed the most. So the top and the bottom. Again, very good. And then final question, when is the total energy the greatest? When is the total energy the greatest?
It's the same throughout because there's no extra force on it.
Assuming there's no frictional losses or air resistance. So if there was friction in this, how would your answer to the third one change? When is the total energy the greatest if there was friction?
Would you subtract the frictional force from the total?
So every time the box moves, the system loses energy due to friction. So when is the total energy the greatest? At the very beginning. Because once you let go and the box moves, you get frictional losses. So the total energy decreases until it finally stops. Until the box finally stops. Okay, next slide. This one should also look familiar. We have a sine wave. This is what it looks like. The height here is called the amplitude. And for us, all these peaks are going to be the same height. All these troughs are going to be the same height. So on top, we call this the peak. On the bottom, we call it a trough. You can also call the top a crest if you want, a peak or a crest. What do you call the points where the 0 line meets the wave? Right? This is a wave. And the wave is meeting the 0 line here, 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 and here. What do you call those points? What do you call those points?
Nodes?
Nodes. Excellent. Good job. That sounded like Ryan. Nodes. N-O-D-E-S.
That's where the lines hit the 0
Yeah.
portion.
Yeah. Those are called nodes. Since we're talking about nodes, what else can we also call the peaks? Remember, these can be called peaks and crests. And these down here are called troughs. What's another name we can call those as well? has to do with nodes. Give you another hint. This is the inverse of nodes. So it is called antinodes. So these are antinodes and those are nodes. Okay. Now, so we have this system in equilibrium, and then Karina comes around and pulls down on it. She can't resist, something she just had to do. She pulls on it and let it go. So then this system will oscillate up and down. What do we call the time it takes for the system to oscillate up and down? We'll call it the box to oscillate up and down. What do we call that amount of time? We call it the period, right? Period is given the symbol tau. And now we have a formula for it. Instead of just timing it, we can now predict it. So the period of a mass oscillating up and down on a spring is given by this formula. 2 times pi times the square root of the quantity m over k. So both m and k are under the radical. Both m and k are both under the radical. What do you think the m stands for?
Mass.
The mass of the, right. And what do you think k stands for?
The spring constant?
The spring constant, good. So we got a question down here. Once started in motion, will the mass oscillate forever? What do you think? Yes, it will oscillate forever unless there are frictional forces or air resistive forces. If you take them out, then this thing will oscillate forever or until somebody hits it. So I think the next
If you take what out?
frictional forces or air resistance. Air resistance admittedly is going to be very small, but
So if you pull on it and release it, it'll just keep going if there was no air resistance and no
Right.
frictional force?
right, it'll go on forever. Something's got to take the energy away, and there's no frictional forces or air resistance. Go on forever. So the next slide, we do an example of this equation. So let's see how you can do. If the mass spring system has a mass of 50 kilograms, which is really, really heavy, and a spring constant of 2 newtons per meter, determine its period. Let's see. Oh, okay. Oh, really don't need to calculate for that.
I got the answer.
Okay,
It would be 31.4.
yes. What if I said the answer was 10 pi? Would I be correct?
Yeah, I know. I'm just looking at it right now. It's literally pi, but with a decimal moved over.
Right.
Yeah. How do you know that just looking at it?
Okay, well, I know m is given as 50, and I'm dividing it by k, which is 2. So under the radical, do I have my, under the radical, I'll put it over here. Under the radical, I got 25.
Okay, right. And then you'll get 5 times 2 and it'd be 10
Right.
pi.
5 times 2 is 10, and then 10 pi. And I know pi is 3.14, so it's just a matter of how much background you got. I've been doing this for a while, so I just look at that and you see the answer. Okay, moving right along. So these look familiar as well. We can oscillate the mass up and down. We can oscillate the mass side to side. We found out what the period is. We've also know what each of these formulas are. We were given the force due to a spring. This, we saw that equation. We certainly saw the potential energy of a spring system. So we saw that, it's nothing new. And we just found out on the previous 2 slides what the period is for a mass on a spring. Good. So see, we're cooking. A lot of this we already have. So now we got a question. If the spring constant is 2, and the mass is displaced from its equilibrium position by 30 centimeters, determine the restoring force. What'd you get for that one? Might be able to do that one in your head if you're comfortable with math. So K is 2 and X is 0.3. Multiply them together, we get minus 0.6, or really plus or minus 0.6, because in this question, it did not say which direction the mass was displaced. It said it was displaced. Okay.
Is it 0.3 because you converted
Yes.
centimeters to meters?
Right, you had to convert 30 centimeters to meters. So that's 0.3 meters. And since it's here and it's fun, why don't we also figure out the potential energy of the system? What did you get for PE? Also, I bet you could do it in your head.
$1.8. Oh, wait, no, because I did not divide it by, it'd be 0.9.
No,
Oh,
but you're closer.
0.3.
No,
Oh, it's squared. Okay.
oh, 0.09.
0.09.
0.09 joules, right? 0.09 joules. Okay, we're cooking. Pendulum going back and forth, another one we've seen. So we just have another formula here. Once again, the L over G. See how they're in parentheses? That means the whole thing is under the radical. So its period is equal to 2 pi times the square root of L over G. What do you think L stands for in this equation? A little bit of imagination. L stands for,
Would it be length,
Length,
yeah, length. And what do you think G stands for?
gravity.
gravity?
There you go. Okay, so now I'm going to give you a homework assignment that you may never get to. And on the other hand, maybe you will. So the homework assignment is if you ever get abducted by aliens and brought aboard their spaceship or to their home planet, what I want you to do is, I want you to take your sneaker off. And I want you to undo the what's that called?
Laces.
The laces. And I want you to hang your sneaker by the lace. And I want you to let the sneaker go back and forth like a pendulum. And I want you to time how long it takes for a complete revolution. What I'd really like you to do is time it for 100 oscillations and then divide by 100. You get a better accurate number. But whatever. So I want you to get tau. So in this equation, you'll get tau because you measured it with your smartphone. And then I want you to plug it into this equation, 2 pi times the square root of L. You know L because it's your shoelace, so you know L. And then I want you to calculate G. Why would I want you to calculate G?
Because it's different in
Right.
space.
If you're on a different planet, it will be G for that planet. On Earth, it's 9.8. On the moon, it's like 1.7. On Mars, it'd be like 3.7. So we want to find out what it is on the planet you've been brought to, okay? And then let me know. Contact me, okay? All right. So next slide is probably a question with this formula. Here we go. If the length of the pendulum is 50 centimeters, what is the period of
Ready?
How many seconds do you get? .4 seconds. Try it. For L, you're plugging in 0.5, right? For L, you're plugging in 0.5 meters. Because you got to convert it. Don't forget that stuff. And then G, you're plugging in 10, like we always do. 10 for G, meters per second squared. And you should get the period is 1.4 seconds. So you see a lot of this is review. Oh, here we go again. These look familiar. So we're going to ask, what form of energy is added to the system? So the ball was right here. And this guy comes around and moves the ball from here to here. What form of energy was added to the system? What form?
Was it potential energy?
Yeah, potential energy was added via work done, via the work done by the man. The potential energy was zero, the kinetic energy was zero. Now, well, the kinetic energy is still zero, but now potential energy is something else, right? MGH. So work was done on the system. When is the potential energy of the system the greatest? So he lets go and the thing oscillates back and forth. When is the potential energy of the system the greatest? And that's going to be at the endpoints. When is the kinetic energy of the system the greatest? As it goes through the equilibrium. So right here. Once this pendulum is let go, it's going to oscillate back and forth. And it will have its greatest kinetic energy when the velocity is the greatest, which is as it goes through equilibrium in either direction. The direction doesn't matter because V is squared, right? The kinetic energy is 1/2 mv squared. So it doesn't matter if your velocity is to the left or to the right, because it gets squared. You get a positive number either way. I
Is there
suspect,
is there a way to write equilibrium like shorthand? Is there a symbol or like,
maybe you can do something like at equilibrium, EQ.
okay,
I suspect that many of you are probably either working on the lab, which is why I normally like to have it done by 6 before class starts. But I'm a wimp and I let you go. So it's just my suspicion. Okay, here we go, waves. Maybe we should take the quiz. Well, we got 5 minutes before the quiz. But this would be a good place to start. Let me just see something here. All right, I can do 1 or 2 at least anyway. So waves, we're familiar with water waves. And I want to talk about waves sufficiently enough so every time you go to the beach, the whole day is ruined because you have flashbacks of this course. So no longer will you enjoy going to the beach. You're going to be hypnotized. Every time you see a wave, you're going to think of this course. All right, so we know waves roll in and roll out over and over again. For the most part, certainly out here, the water really doesn't move. You can make the argument that the water moves here in this region, but that's because you got all kinds of additional frictional forces. But out here in the water, in the ocean, bay, the water's really not moving. It pretty much stays still. And what moves is the energy going through the wave. Now you can make the argument, if you know, but that the water molecules actually do move. They move circular pattern like this as the wave goes. I mean, I'm sure you've seen a seagull floating in the water. See, so now on, when you see a seagull floating in the water, you're gonna think about this course. If you see a piece of driftwood bobbing up and down, again, you're gonna think about this course. And what you're gonna notice is these don't move on their own. It takes a long time for them to move across the water. You'll see them move up and down a lot. Maybe to the side a little bit, or if given a long period of time, you may see, for instance, the driftwood move, but that's because of additional currents in the water hitting and moving, generating additional forces. But for the most part, the water on average stays in the same spot. This oscillates around. Energy winds up going through the water. And when the water is very shallow, again, you get an increase in forces and the molecules wind up moving more than they would out here. Here's another example. You have a slinky stretched out. And you curl a couple of the curves with your finger, and then you let them go, and you watch them oscillate back and forth. So it's very dense here and not dense as here. And this density will wind up going, no, can't do that, let's see. And then this part will wind up going back and forth, finally making its way to the other side, bouncing back and coming back. So the question is, with one end of the slinky fixed, a simple forward and back motion produces a traveling wave, or in this case, really a traveling pulse. It creates a pulse, and the pulse moves down slowly as it oscillates back and forth. It winds up moving forward, we'll hit this, and then we'll wind up moving back. So it's the pulse that's going back and forth. What is moving? Well, the pulse moves. Energy is what's being transferred down the line, energy. The medium itself, the slinky, really doesn't move as a whole. Just like the water as a whole, at least out here, doesn't move. Sorry about that.
Bless you.
Thank you.
Bless you.
Bless you.
One more time. Local compressions. I just talked about this, okay. So the region of compression moves along the slinky. The slinky as a whole doesn't move. All right, a slide of words. I try my best to avoid a slide full of words. It's nothing more than turns off a student than a slide full of words. But let's just go through it. I think it's the first one we've seen. The wave or pulse moves through the medium. That was the previous slide. The medium itself does not move. Again, the previous slide. Water moves towards the beach, but water doesn't accumulate there. It winds up going back, right? Unless you got some kind of incredible storm. A pulse moves in a slinky, but the slinky remains stationary. So, in general, the disturbance moves with the speed determined by the medium. So far, we've talked about things where the speed doesn't really matter. The medium doesn't really matter what the speed is. We talked about a guy running or a car moving. They had speeds independent of the air or the road. Now with these kinds of waves, the speed of the wave will depend on the medium. The medium now is a big thing, so you gotta think a little bit differently. The speed now depends on the medium. So I have two questions for you that I'm not gonna answer right now. I want you to think about them. One, will the pulse travel faster if you stretch the slinky more? So you have the slinky stretch a certain amount, comfortable amount, and you make a pulse and make it move down the line. Will that pulse move faster if you stretch the slinky more? And secondly, what if you replaced that slinky with a heavier slinky? What will happen? So what you're doing here is you're really changing the medium. You're changing the medium, and the speed depends on the medium. So it'd be good to try to think about what the answer is. How would the speed change? Would it increase or decrease?
So I think I understand it. Should I give it a shot, or did you want to wait for?
Not yet.
Later?
Not yet. By the end of the night,
Okay.
you can, if you wish, but not yet. I want everybody to.
Okay, I'll hold on to it.
Thank you for asking. Okay, so energy is carried along by the pulsar wave. We also said that in the previous slide. We have two kinds of waves. We have something that's called a longitudinal wave, where you have a pulse, and the pulse oscillates back and forth, but pretty much moves forward. It's going to wind up going back and forth as it moves. That's a longitudinal wave. Then we have a transverse wave. Transverse wave oscillates up and down. See, this one's oscillating back and forth in the direction of motion. That's longitudinal. Transverse kind of even sounds like a transverse. It oscillates perpendicular to its motion. Its motion is this way, but it oscillates up and down. Can you give me an example, besides a slinky, of a longitudinal wave? That should be right up your alley. An example of a longitudinal wave. Even if you don't know, take a shot. Go ahead, Caitlin.
I was thinking an accordion, but it can go up and down too. So
Yeah, depending on how you orientate it.
yeah.
And that's really gonna move because you're moving it. This, I'm talking about, once you start it, it goes on its own.
Is sound?
Yeah, excellent. Good job, D. A sound wave, that's why I said it's right up your alley. Sound waves are longitudinal waves. I guarantee you're gonna get that. Can you give me an example of a transverse wave?
like, would the movement of like the tectonic plates be transverse?
No, no. That's a good guess, but no, sorry.
Light waves.
Oh, who said that?
Kiara, sorry, I have a loud background here.
Oh, that's excellent. A light wave. I did not expect that to be an answer. How do you know that a light wave is a transverse wave? How did you know that?
I just kind of remember that from back in high school.
Okay, no, she's right. A light wave is a transverse wave. I was hoping you guys would say water waves because we just saw, you know, you got the wave going up and down and what's happening, it's moving this way, right? The wave winds up moving, water waves, but she's also right, light waves as well. Okay,
Wait, why are light waves like that? I feel like I remember it, but I don't remember like why light travels like that.
light is something that's made up of two kinds of waves, an electric field wave and a magnetic field waves. And each of those are transverse waves. They combine with each other to produce each other over and over again. I'm not sure I can say anything more than that,
Okay.
what they are. We gotta think about that. I'm gonna write it here so maybe I'll remember.
Professor,
It's a light, a transverse wave. Besides something simple like it's made up of transverse waves. That's not a good answer. I gotta think about that. Okay, yes, Lindsay?
yes, that was me. I just wanted to let you know that it's 6:30.
Oh, okay, good. Good. So then let's stop and take the quiz. Good luck, everybody. So periodic wave. We have a wave. You have a slinky on a tabletop there, and we're sending down individual pulses. We're sending down different pulses. So here's a pulse, here's a pulse, here's a pulse. We're sending one pulse down the line, one after another. So a series of pulses produced at regular times generates a periodic wave on a slinky. So here we're starting to see waves being generated. We were sending down pulses. Now, by repeating the pulse at regular intervals, we now have waves. And here are symbols you should become familiar with. This symbol, does anybody know what this symbol is called? You're going to see a lot of this in ultrasound.
That's lambda.
Yeah, it's called lambda. Very good, lambda. L-A, it's another Greek letter, M-B-D-A, B-D-A, lambda. It stands for wavelength. It stands for wavelength. We'll go over that, it'll come up. Then period, we already went over period. Frequency, we already talked about frequency, and amplitude. Remember, amplitude is sometimes given by the small a as well. So you got to take a look at the diagram and see what the author's doing. Oh, let me just mention wavelength here. So we have a wave, something like this, and it goes on and on and on, as waves do. The wavelength is the distance from one point on the wave to the exact duplicate of it. So for instance, a wavelength is from the peak of one wave to the peak of another wave. This distance would be called a wavelength. But of course, the wavelength of a wave is a distance. So it doesn't really matter where you start or where you end. It's the relative distance that matters. For instance, instead of doing it from peak to peak, which is probably the easiest to do, it can also be done from trough to trough. It could be done from any point. You can start anywhere you want. You can start anywhere you want. For instance, we can start here. any way you want to start. Then you have to travel along the wave till you get to the same point. Now this here is not the same point, because this one here is over the peak coming down. So you would have to continue going till you came down. So from here. So you can also call from here to here a wavelength, lambda. That's also a wavelength. So a wavelength is an actual length that describes the wave. It's most easily written as from one peak to another peak, or sometimes from a trough to a trough. That's just for convenience. But it doesn't really matter where you start. It's a length. You just have to go to the next identical point on the wave. So that's wavelength. Okay, we're moving right along. Next slide, a wave pulse. A pulse is a disturbance that moves through some medium. You know, we saw water wave, we saw a slinky wave, or pulse in this case, but the medium itself goes nowhere. The medium itself goes nowhere. It's the energy that's going through, the pulse that's going through. A periodic wave pulse consists of several pulses spaced at regular intervals. See, that's the next thing you have to get comfortable with. We can draw our waves as a function of distance, and this would be height, for instance, or we could do it as a function of time. So this would be called spatial, and this would be called temporal, as in time. Temporal or spatial, depends on how you're looking at it. And it can be the same wave. The same wave. For instance, if this is height, the height changes. Think of a water wave. Think of a water wave. And you're on the beach, standing on the beach, looking out. And at one instant in time, you took a snapshot, a picture of the water waves. So as the distance goes, you see the heights of the waves as the distance changes. You look to the left, you look to the right, and you see the waves. So this would be then height versus distance of the water wave. You're looking at the horizon and you see all these waves. On the other hand, you could look at just one point. Perhaps you're watching a seagull or a piece of driftwood bounce up and down. And you're watching it as time goes by. So as time goes by, the wave doesn't do this, right? Sorry, it's the second time tonight. The wave doesn't do that because it's with time. Yes, the wave goes up and down, but the time is moving on as well. So what's seen as the piece of driftwood is bouncing up and down, that's happening as time is going on. So you see, you come up with the same kind of wave, but using different ordinance in space or time. So this is called spatial, this is called temporal. The idea now, this is a big equation here. This is the wave equation for us. It is V is equal to lambda F. V is equal to lambda F. Now we just said what lambda is, so we know lambda. We know frequency from another chapter, and we know what speed is. So we're familiar with this formula then. V is equal to lambda F. And keep something else in mind, that when it comes to waves, the speed depends on the medium that the wave is going through. So what I'm saying is, if you have a water wave, and you have the wavelength of the wave, you can calculate what the frequency is because the speed of the water wave will depend upon the medium, the water. So you know this by knowing the medium. If you change lambda, you don't change the speed. This is important. If you change lambda, you don't change the speed. What you wind up changing is the frequency. V only depends on the medium. Okay, we're going to use this equation a lot. All right, let me just go one more slide, because then it's the question, I think, and then we'll do the review. All right, so we're let's just do one to cement our understanding. If a sound wave has a wavelength of 50 centimeters and a frequency of 7 hertz, calculate its speed and period. Well, try it on your own. We want its speed, so we want V. You're going to use V is equal to lambda F. Try this on your own. What am I going to put in for lambda? 50 centimeters? No, I'm going to put in 0.5. I convert it to meters. What do I put in for the frequency? It's right there, 7 hertz. So my speed then becomes 3.5 meters per second.
We move for centimeters to meters, we move it 2 points over.
You divide by 100.
Oh, divide by 100. Okay.
And then next one is we're going to calculate its period. Well, we're given this formula here. F is equal to 1 over tau. But with a little bit of algebra, you can see that tau is equal to 1 over F. And we're given F. So then tau is equal to 1 over 7. So plug that into your calculator, and what do you get? Like 0.14 or something? Yeah, 0.143. So tau is equal to 0.143. Now it's tau, so you know it's going to be in seconds, but how do you get seconds out of hertz? So 3. Let me change color. Well, hertz, you may recall, really is cycles per second. Cycles, I'm just going to write CYC because you see I'm having trouble getting with the mouse. Cycles per second. Now what you're doing is cycles per second is on the bottom. So when you divide 1 by cycles per second, you wind up getting seconds per cycle. And if you remember the other day, we talked about how we generally leave out the word cycle. So the units of lambda are meters, but it's really meters per cycle. What about tau? The period, well, that's really seconds. But no, once again, it's really seconds per cycle. And what about frequency? Frequency, we call it hertz. But what's a hertz? Hertz is?
Cycle per second.
Yes, cycles per second. And just generally leave out the word cycle. You see, these two are inverse. Even the units, seconds per cycle, cycles per second.
So is I'm just like confused because like the chart says frequency equals 1/tau, so
So mathematically, we get frequency is 1/tau.
and we're looking for period, so
We multiply both sides by the period. What I do to one side, I have to do to the other. These cancel, and I'm left with 1 on this side. So now what I do is I divide both sides by frequency. They cancel, and I get frequency over here. So tau is the only thing that's left, right? Tau is what's left. Tau is equal to 1/frequency.
okay,
Frequency
I
is
see it.
tau, and tau is 1/frequency. Okay, so let's do the quiz. Review the quiz. So let's stop share on this. Let's go back to share. And Karina, would you read them to me again, or somebody read them to me? The quiz questions?
Sure, let me pull them up.
Got one of them, Ryan. I'm not sure which one.
All right, we'll go over it.
I have the questions up if you want them.
Somebody read them for me.
Okay, number 1 is you are pushing a shopping cart straight across a level floor, a total distance of 10 meters. You apply a constant force of 17 newtons in the horizontal direction. Calculate the work done on the cart by you.
Okay, so you got the cart. You get a horizontal force, you're pushing it, and the cart is moving 10 meters. 10 meters. Our formula for the work done is equal to force parallel distance. I tried to draw this with the force parallel to the distance being moved. They're in the same distance, so we don't have to worry about any components. So I can just say, use the full force, which was 17 newtons, and multiply it by the total distance, which was 10 meters. And I get 170 Newton meters or joules, but again, you didn't have to put in the unit. Look like most people got that one. So we can move on. Whoever's nice enough to read question 2.
Micah is riding a sleigh with a speed of 5 meters per second. If the total mass of Micah and the sleigh is 50 kilograms, find the kinetic energy of the system.
Oh, okay. Well, kinetic energy is equal to 1/2 mv squared. So we plug in 1/2 m is 50 times 5 squared. So we get half of 50 is 25, multiplied by 5 squared, which is 25. And 25 squared, that's essentially what that is, right? 25 squared is 625 joules.
I'm confused, but for I think a different reason.
Uh-oh, okay.
No, it's. Oh man, I'm really. So I got both these answers.
Good.
But on the quiz, I got a 7 out of 10.
7 out of 10.
Which means
You got a 3.2.
either I made a typo or I had to have gotten one of these wrong because the last question was worth 4.
Right. Okay.
Did you go to your grades? You could look what you actually input, Ryan.
Oh, you can? Where do I see that?
Yeah. If you go to my grades and then you click the exam, like where it says your grade and it'll say 7 out of 10, click on the exam.
Wait a minute.
And then
Hold on a
you
sec.
can, where the grade is, you can click, there's a link and it'll show you the quiz and then your answers.
I believe it shows you like an hour after it's been released because I don't see
I-
my actual.
I
answer
guess
yet.
I guess I'm paranoid. It now says 10. Never mind. I'm sorry.
Okay. Hey, if I can make mistakes, anybody can make mistakes. I can.
I feel like such a fool.
You don't sweat it. Okay, so number 3.
Okay, number 3. A block slides down a frictionless hill from a height of 12 meters. Determine the height of the block when its speed is 10 meters per second.
Okay, so the box is up here. Initial speed is 0. It winds up sliding down. And at some point, we don't know the height. We don't know the height. We want to find out what the height is. But the speed at that point, is, what did we say the speed was?
You didn't,
Oh, I didn't know. We know the height.
but we have to assume it's 0.
I'm sorry, read the question again, please.
It says, a block slides down a frictionless hill from a height of 12 meters.
Good.
Determine the height of the block when its speed is 10 meters per second.
Okay. So this is what we got. The block starts out at the top, 12 meters high, slides down. It's going to pick up speed as it slides down. And we want to know how high it is when the block is moving at 10 meters per second. It's frictionless, so there's no work being done. So we can use our simplified formula. E initial is equal to E final, conservation of energy. E initial, the only energy we have initially is potential, but since we're still kind of new to this, let me do the whole thing. We have potential energy plus kinetic energy plus work is equal to potential energy plus kinetic energy. Since I got potential energy here and potential energy there, and they can be different, I gotta use different symbols. I'll just put primes on the finals. Or you can write subscripts after. It's just easier for me to write a prime. When the block is here, it has potential energy, so I'm gonna write mgh. When the block is there, the speed was 0, so kinetic energy winds up going to 0. There's no work done, no work was mentioned, and the surface is frictionless, so there's no work done. At the end, we do have potential energy because we want to know what the height is. I mean, the height could be 0, but we don't know that yet, so we got to write in mgh. But this h is going to be different than this h, we assume, because the speeds are different. So I got to use a different symbol. So once again, I'll just use the prime. It's just easiest to write. Plus the kinetic energy. We know we have kinetic energy because we have speed. So I write down 1/2 mv squared. Okay, let me slow up. Everyone's okay? So now, let me just rewrite it. I get mgh equals mgh prime plus 1/2 mv squared. The h's are different, so I can't do anything with them. The g's are the same. The v, well, there's only one v, not much I can do with that. But each term has an m. Each term has an m, so I can cancel the m's. Divide both sides by m. And now I wind up with gh equals gh prime plus 1/2 v squared. Now it's time to plug in. Really can't do too much else. I could combine the g's, but might as well just plug in at this time. G we know is 10. The H initial is 12, right? To the left of the parent of the equal sign is the initial, to the right is the final. Equals, on the other side, G, so that's 10 again. H prime, we don't know. That's what we're trying to find out. So I'm going to leave that as my variable. Plus 1/2, and we're told V is 10 here. So continuing, I get 120 there equals 10H prime plus 100 divided by 2 is 50. So I can subtract 50 from both sides and I get 70 equals 10H prime. Divide both sides by 10 and I get H prime is equal to 7 meters. Everybody's okay with that? So it's conservation of energy. You plug in. There was no work. Kinetic energy initially was 0, so we just had potential. And set it to the other side. The other side we have both potential and kinetic. Took out the m's, which is interesting. When you're dividing through m, what you're really saying is it doesn't matter if it's a sleigh going down or a house going down. The object doesn't matter. No matter what object, it could be an ant going down, sliding on its butt or whatever. Still going to be the same height, you get the same speed. They're saying the mass doesn't matter at all. It could be anything. Okay? We just got to take look for 7:24. So we got about a half an hour. Any questions? More? No. Just keep going with the PowerPoint. Okay.
Can we go over the stuff for the test?
Yes. Let me finish those couple of questions on the PowerPoint.
Okay.
And then we'll do that because this ties in. It ties in. So the previous one, we were using this formula here. And we got it here and we found out what the period was and the speed. And I think the next question is something similar. Test your understanding. If a sound wave has a wavelength of 25 centimeters, so again, you have to convert, right? And a period of 400 seconds, calculated speed. Oh, look at this typo. It's supposed to be frequency. Calculated speed and frequency.
Your screen isn't shared, Professor. I don't know if you were,
Oh,
if
so
you
you
wanted
didn't-
it to be.
I changed that. That's good. Why can't I do that? Okay, so I got to share my screen. Thanks for telling me.
You're welcome.
So now you see it, hopefully? Yes, you do. Okay, so sound wave has a wavelength of 25 centimeters and a period of 400 seconds, calculated speed and frequency. I'm going to use this formula here for speed. Try this on your own. I'm hoping you can do it. I'll start to do it here. And only look if you need help. Try to do it on your own. I mean, you're only supposed to be looking if you get stuck. This is a slow wave. 0, 0, 0, 625. Surprises me when I gave you a question with such a small number. I guess to change things up, I guess that's what I was thinking. All right, frequency is 1 over the period. Period was given to be 400, so the frequency is 0.0025. You can do the speed, lambda times f. So 0.25 is the wavelength. And we got to divide by 100 times the frequency. And I get 0.000625. How would I do that in scientific notation?
How did you get the 0.15?
That's supposed to be a 2, I'm sorry.
Oh, okay.
It's writing with the mouse. 0.6, so that's 6.25 times 10 to the what?
-4.
-4. Okay, I'm gonna count.
Okay. My calculator put that down and I was just like, what?
Okay, that's good to know. So that's
Yeah.
1, 2, 3. Yeah, you're right. 10 to the -4. Let me show you another way of doing this. You see this formula? I'll change color. You see this formula right here? It may come in handy that you understand that that formula is the same as this formula. V equals lambda over tau. It's the same formula, so we get frequency is 0.0025. Why does it have to be that one? It's all right if you're writing it on the board, but writing with a mouse. 25 divided by 400. We should get the same answer. Let's see if we do. 0.00. Oh no, that's wrong. Lambda is not 0.0025. No one yelled at me. It's 0.25.
What?
That, that.
Oh yeah, lambda is 0.25 and the frequency is 0.0025.
Lambda is 0.25 and the period's 400, so you can use this formula and we should get the same number.
I got 1600.
1600. You gotta flip it.
Oh, yeah.
So I get the same number. 6.25 times 10 to the -4. Same number. Okay. And then the next slide, I think, is something else. So someone asked to, okay, so this is where we can stop. Let me write this down. So we did quiz 7. We're going to do exam 3. PowerPoint, chapter 15, up to slide. This is slide 19. We did up to 19. Okay, and then review and test. So I can stop this. We'll come back here. And share the camera. Hey, I think it was Ethel who asked me to do some, had questions about the exam. Ethel, what would you like to cover?
Just mostly the formulas that I need to remember.
Okay, so that's really all of them. That's got to be my answer, right? All of them up until the end of chapter 6. 5.
So mostly chapter 5
Okay, so let me just pull out
and 6, I guess.
chapter 5 and 6. Okay, so let's go for that.
I thought chapter 6 was not on this exam.
Chapter 6 is, you're right, chapter 6 is not on this exam. So
Okay, then chapter 5.
Chapter 5. Okay, so let's go to chapter 5. We're gonna go right to. I've got my thing on, so let me go to chapter 2. Okay.
I do have like a little mini question. My textbook, I realized like last night, they're not the same questions as yours. It is the 9th edition of Physics of Everyday Phenomena, but it says instructor's evaluation copy. So
The same thing. It's just that they send that book to the instructor, but expect it back.
okay.
So you say the questions are different, chapter 5? I think the questions are the same, but the numbers are different. Or maybe they're in different order. So let's
They're
see.
like pretty much the same question, just like different numbers is what I noticed
Yeah.
last night, like different,
Yes.
yeah.
Yeah, I have that because I have, I think, the newer edition, and it's usually been the same questions, just a little bit of a different number that
Right.
they use. So
Yeah, you can still use the SB problems, just that you got to put in your numbers.
Okay, just wanted to make sure that I got some not good copy.
Okay. Put this one back. Okay, so we were gonna go over this. So the first thing we started out with in chapter 5 was the idea of centripetal motion. An object going around another object at constant speed. So the speed is constant, but notice the direction changes. So the velocity changes, but the speed doesn't. The centripetal acceleration, we talked about how the velocity vector changed, and that the difference between the final and the initial velocity vectors winds up pointing towards the center, which is why it's called centripetal, which means center seeking. So the velocity vector changes in such a way that it points towards the center of the circle. So in this motion, the speed is the same and the radius is the same. And we wind up getting this formula here. The centripetal acceleration is equal to the speed squared divided by the radius. And then from that, we moved on to forces. In physics, we like forces. We like knowing why things happen. And the object here is changing its direction of motion because of forces. What force? The centripetal force. Now remember, the centripetal force is not a new force. It's the sum total of all forces that keep the object in the circle. So in the case of a ball going around on a string, it's the tension in the string that generates the centripetal force. For the moon going around the earth, it's the gravitational force of the earth on the moon that keeps the moon locked in. So look at this. Let me just mention this. In case it comes up at a party. You have the Earth, and you have the moon going around the Earth. We know there's a gravitational force of attraction between them, so why doesn't the moon fall down and hit the Earth? There's a gravitational attraction force between them. Why don't they combine? And it's an unbalanced force, isn't it? It's only one force. It's the force of gravity between them, which we call the centripetal force, because that force of gravity is keeping it in the circle. But we know if we have any two objects, even two people, and there's only one force on them, they're going to wind up colliding. They're going to accelerate towards each other. So why doesn't the moon fall down and hit the Earth? There's only one force. It's unbalanced. So we know F equals ma. The moon should fall down and hit the Earth. Why doesn't it? Anybody?
Because of gravity.
I'm sorry, you broke up a little bit. Yeah, you froze out. I see Caitlin moving, but I don't see you.
Gravity? I don't know.
Okay, so gravity is what's trying to make the two accelerate together. What happens is,
Can I try?
say it again?
Can I try to answer?
Yes.
Is it because they both have forces acting on each other? No?
No.
Okay.
Nice try. I'm glad you tried, right? I like my students to try. But as the bankers would say, no loan.
Can I give it a shot?
Yeah, no, he's going to get the answer. Should I let him? Yes, absolutely, Ryan.
So even though gravity is trying to pull the moon towards the Earth,
Yes.
because of the moon's motion, all gravity does is change its direction around it.
Yes, yes, exactly. So let me say that in a little bit differently that I think might be helpful for some of the students. What's happened, if we forget about gravity just for an instant, we know the moon has a speed, and we know, because we learned it in this chapter, that the speed of the object in centripetal motion is always perpendicular to the radius. Hopefully you remember me saying that. The speed of the object is perpendicular or to the radius or tangent to the circle. So that means we know the moon is going this way. If the moon is going that way, and we forget about gravity for a second, isn't the moon getting further away then? Pythagorean theorem. Radius and this distance, right? This squared plus this squared equals this squared. So just due to the speed of the object, which is what Ryan was saying, the moon is getting further away. But for it to be in orbit, the force of gravity is strong enough to keep pulling it back in. So the moon wants to go away, but gravity pulls it back. The moon wants to go away, but gravity pulls it back. Keeps doing that. So you wind up getting a circle. So the moon is continuously falling towards the Earth, but at the same time, the moon is getting further away. And the net result is it stays the same distance. It's really more elliptical shape, so
Quick
forget about that
question
detail.
on that. Is that kind of how centrifugal force works?
Centrifugal force?
Yeah.
Centrifugal force, let me give you an example of what that is. Let's say you have a pivot point, and because we do this in class, when time permits. In this course, not too often. And there's a board, and you sit on a board, and this thing rotates, as in the circle. It's the same kind of idea as the moon going around. So the moon would be wherever you're sitting, and this thing's rotating. And you try to throw a piece of paper, garbage, into the garbage can as you're going around. You try to throw the ball into the crumbled up piece of paper into the garbage can, but unless you are smart enough to adjust for your motion, you're always going to wind up missing. That's what centrifugal force is.
I think I see. Thank you.
I can't hear you.
Oh no, I was just saying. I think I understand the diagram. Thank you.
Oh, okay. Okay, well, then moving on. The next formula in the chapter I said we didn't have to worry about. If we had a little bit more time, it'd be fun to get into Kepler's 3 laws, but we really left them out. I mean, I gave you a very brief overview of Kepler's 3 laws. If you remember, one was equal areas and equal times. Another one was the orbit is elliptical, not circular, with the sun at one focus. And the third one was as the harmonic law. It's the relationship between how long it takes the planet to go around the sun with respect to its distance, and that's a constant for every planet. And not only every planet, it's a constant for everything in the universe. This, since you brought it up, this is where dark matter. Have you heard of dark matter? Have you heard of dark matter?
I have.
Okay, so what reason why that came in? An astronomer was looking at galaxies. Galaxies contain hundreds of billions of stars. Well, some are smaller, but you get the idea. And they kind of look like, well, they have all different kinds of shapes, but these elliptical ones. And the idea is this formula should work for stars going around. How long it takes the stars to orbit the center of the galaxy should depend on its distance, according to this formula. The same as how long does it take the planet to go around the sun, or the moon to go around the earth. It's all supposed to be related to this formula. So if I remember right, it was a 1. Anyway, so and she found out that this law didn't work for galaxies, for stars going around the galaxies. And they pondered and they pondered, and what they found out was, by using some other laws, that there must be a lot of missing mass. If you had missing mass in the galaxy that we can't see, it could make up for the difference of what was predicted versus what was observed. So they went to other galaxies and they found the same thing, and the same reasoning would apply. If there was dark matter we can't see or detect in the galaxy, causing extra forces on the stars going around, it would make up for the time difference that they saw. So that's where dark matter finally came in, is by observing distant galaxies. Okay, so then moving right on. This one we did. In fact, I believe, I wouldn't bet my life on it. Well, maybe I'd bet yours, but I wouldn't bet mine that this is on the exam. In one form or another, I'm pretty sure I put that. If I didn't, I meant to put it on. Because I went to every single person and I made sure that they knew how to do that. I broke you into breakout rooms, so this formula, I don't know if you want to go over that.
Yes, please.
Over it, yeah.
Yeah, we did a number of examples, right? We did Ryan, and I think it was Olivia and Caitlin. I forget who the girls were. No, I think it was 3 girls. I don't remember what it was, but we talked about the force of
It was 3 girls. I was not involved.
eating pizza pies and all that kind of stuff. Ryan, were you involved?
He was.
No, I was not.
Oh, okay.
It was Caitlin, Olivia, and Karina, I think.
Okay. All right, so we have a formula, F universal law of gravity is equal to the gravitational constant of the universe multiplied by the two masses involved. So this is for the force of attraction between any two massive objects. When I say massive, I don't mean big. I mean anything that has mass. So we can talk about two atoms. We can talk about two atoms. And we divide it by the distance between them squared. So that's what's used. Does anybody remember the value for G? Just to save time.
Was it 6.67 times 10 to the negative 11th milliseconds per, yeah, the units I'm unsure about.
Newtons meters squared per kilogram squared.
That was.
M1 is just happens to be the mass of one object. M2 is the mass of the other object. And we know from Newton's third law that the force of object one on object two is the same as force of object two on object one. Speaking of that, one thing I wanted to ask, and I didn't get a chance, so let me ask. Will I see? Anybody want to question it? Question? How about Ashley? How about Ashley? Are you there? If not, that's okay. Really? Ryan is going to get it, I'm sure. So.
Yes, I'm here.
Do you want a question or?
Yes, sure, I'll try.
Okay, so you're driving down Sunrise Highway and you're going 55 miles an hour like a good person, right? And you're waving to everybody, you're friendly, and you're driving down. Then all of a sudden, this gnat goes by, a little mosquito goes by and hits your windshield and splatters all over your windshield. Now it's small, so it's not too bad, but it's definitely still gross. So now my question to you is, since nothing really happened to the car, you didn't even know, you just happened to see it at the corner of your eye on your front windshield, but the mosquito splattered all over your windshield. In that case, which experienced the bigger force, the gnat or your car?
I would say the gnat.
Yes, most people would. Sure, Brian wouldn't. That's why I didn't want to call him, because it's funny if the students don't get it, right? So it winds up being Newton's third law still again. The car experiences the same force that the gnat does. So the answer is F equals ma. So you have, in the case of the gnat, the mass is very small. So the acceleration must be big. In the case of your car, the car's mass is very big, so the acceleration's got to be very small. That's how that works. So it seems as if the gnat experienced the greater force, it winds up the force is the same. The reason why the gnat splattered on your windshield is because of the acceleration it encountered, it felt. The acceleration was very great because its mass was very small. On the other case, the acceleration of your car due to the collision with the gnat was so small because the mass of the car is so big. Again, so Newton's third law is still the same. All right, so I'm sorry, as usual, I get sidetracked very easily. So we were going to do this problem. Oh, we didn't have a problem to do. We got to make one up. Okay, so let's find out the force of attraction between what two things? I need a mass of one object, a mass of a second object, and I need a distance. Or you give me the force. One of these, right? It's always one equation, one unknown. Which one of these four do you want to look for? I think in class we always look for this one, I think. I'll do the problem. You just tell me which one you want me to solve for.
Whichever one's on the test. No, I'm just joking. I guess like maybe can we do like mass 1, like just to see?
Okay, so we don't know mass 1. Mass 2, let's just use easy numbers, 100 kilograms. Or, let's use again an easy number, let's use 10 meters. And let's have the force of, it's going to wind up being very small. So let's make the force small. 0.001, a thousandth of a Newton. That's what that is. I mean, you could plug in, right, 10 to the minus 3 if you wanted. In any event, let's write down our formula. F is equal to G M1 M2 over R squared. And now we're going to plug in. F we know is either 1. I'll put in, so I think you prefer it, I think, 001. That's what force is. Equals to G. G is this number. I'll put that in parentheses. 6.67 times 10 to the minus 11th. Mass 1 we don't know, so I'll just leave it as mass 1. Mass 2 we said would be 100 kilograms, just to keep the numbers easy. And the distance, we wanted this 10 meters. I should have made it a lot smaller, but no big deal. But R is squared. R is squared. So I got to square 10. So we got to solve for M. Let's rewrite this. We can do it different ways. So 0.001 is equal to 6.67 times 10 to the minus 11 times 100. On your calculator, you should get 6.67 times 10 to the minus 9 when you multiply those two. But then we still got M1, so I write down M1. Now we're going to divide this by 10 squared. So what do we get now? Just rewriting it. This is 10. I'm going to write down 10 to the minus 3. That's what that is. Now this is equal to what? 6.67 times 10 to the minus 9 divided by 10 squared. Remember, when we divide powers of 10, we subtract the exponents. So I wind up getting 6.67 times 10 to the minus 11th times M1. Do you have questions?
How did you get -9?
Okay, so this 100 is really 10 squared. When we multiply powers of 10, we add the exponents. So minus 11 plus 2 is minus 9. Or you can just do it on your calculator. We'll do it on the
I
calculator.
did, but I got -8. That's what I'm asking.
No, this is 2. You should get minus 9. We'll do it on the calculator as well.
Okay.
Now I got to, that's it. So we're down to this. So now I got to divide both sides by 6.67 times 10 to the minus 11th. Divide this side. So that cancels. And I got to divide that side. What I do to one side, I have to do to the other. 10 to the minus 3 divided by 10 to the minus 11. So that's minus 3 minus a minus 11, or you can add 11. So minus 3 plus 11, that is 8. So it's 10 to the 8th divided by 6.67. So we got to do that on the calculator.
I'm sorry, it wouldn't be 10 to the negative 14th, because you have 10 to the negative 3rd, 10 to the negative 11th.
So we got to subtract exponents because we're dividing, right? So it's minus 3 minus a minus 11. So it's minus 3 plus 11.
Oh, that's right. Okay.
So I get 1.499. So for all practical purposes, call it 1.5.
Excuse me, Professor, I have a question. It's 10 to the negative 9 over 10 to the positive 2. So So would it be -7 or it's still -11?
Okay, so it's here.
Yeah, I'm talking about there.
So we get -9, -2 equals -11.
Oh, okay. Because it says 10 to the second, so I didn't know that you would -2. I thought you would add 2.
Okay, good question. Let me clear that up. When you divide, you're going to subtract. When you
Okay,
multiply, you're going to add. So in both these cases, I had to subtract because I was dividing. Minus
okay, thank you.
is dividing. Good question. I'm glad you asked it. Now you know. Okay, so that's what I get. So if I push the right buttons and all. So now let's do it with our calculator. Since Ethel asked, what calculator do you have? Do you have like the graphing calculator? Or
Yeah, TI-84.
So you have the graphing calculator. Okay, so let's do it on the graphing calculator since you asked. Put the light on. Okay, get rid of the glare. Turn this on. Clear. Okay, so we're here. Depends on really where you want to begin. Let's begin with this step here. So I'm going to put in the 0.001. 0.001. Can you see that? Yes. I'm going to move it over a little bit more. And now I got to divide by this, and I got to divide by that, and I got to multiply by this. First, let's divide by the 100. I want to get M1 by itself. M1's being multiplied by 100, so I got to divide by 100. So I'm going to divide in my calculator. I'm going to divide by 100. But I also got to divide by this number. Now that's the tricky one. So I divide again, and I put in 6.67. Remember the EE button, for me, it's above the quote here, or column, whatever you want to call it. Move that over a little bit. So second EE, it was -11. So on this calculator, on this type of calculator, you have to press this button, this minus button, not that. You get screwed up. You have to press it this one because you're not subtracting something. You're putting something to a power, and it's to the -11 power. There's a bunch of glare. A little bit better there. And now I still have to multiply by 10 to the 2, right? M is still being divided by 10 to the 2. Well, 10 squared. It's being divided by 10 squared, so I got to multiply both sides by 10 squared. So let me take my calculator and multiply, so it's times 10 squared, 10, and then the square key, hit equal. And essentially what I get, 1.499, or I put in scientific notation. Oh, on here I have to change the mode. Well, let me show you how to do that. You hit the mode key, and you get a bunch of stuff. I want sci-fi, so I can scroll down, but I don't want to scroll down. I want to scroll over. So I go back up to the normal, I go over one to sci, and I hit enter. Now psi, now I know I'm going to be in scientific notation, so now I say second quit to come out, and I hit enter, and now I have my number in scientific notation. Essentially 1.50 times 10 to the 7th, and that's what I got the first time I did it.
How did you come out of the scientific notation again?
Okay, I did second quit.
Second quit. Oh, okay. And then press enter?
Well, you got to press enter first, and then you do second quit. And then you can hit enter again if you want, right. And it will put it into scientific notation.
And that's when you get the, okay. Okay, I see it.
Good.
In the beginning, you like divided. I'm so confused with how you did it in the beginning.
Okay, first,
Yeah, that's what
Wouldn't
threw
it
me
just
off.
do-
I was like,
Like for me, I would just like multiply like the 6.67 times the 100 and then have like that M and then divide it, or you can't
you
do
can do
that?
that too, sure.
Okay, I'm just like
Just
so
do
confused
more.
with how you're doing it.
Yeah, I didn't even include the point.
Can't you even like cancel out? No, well, can't you cancel out the 10 square? Did you do that? I'm just so
Oh, I
confused.
didn't, but you
I
go.
just quickly would like to bring, it is 8 o'clock.
Yeah, so if you
Are we on
want to
time
begin,
limit?
begin the test, go ahead. I'm gonna finish with this and then that's it. So I don't want to be giving away answers while the test is on. So you can, 10 squared is 100, so you can cancel that. You can do that. And then just divide both sides by this. And you find out what the answer is.
Okay, I got it.